Okay, here we are in the lab again. So welcome to episode 18. So we're going to have to get our functions for our reading and writing to the SRAM written out in code. And we're going to have to get our interrupt working so that when we do have an interrupt from a busy signal, that we wait and write the data when the busy signal is no longer asserted, so that we can guarantee that when we write to the SRAM, that data is really getting written to SRAM, regardless of what's happening on the other side. That's very important. So we have main brain writing continuously on one side and the IO board writing continuously on the other. So that's never going to happen. Well, almost never going to happen in the real world. So you're just going to get a little blip here and there, but we want to make sure the most extreme case is handled so that we know that our data is really going to be in there. And so it's like building a house of cards. You don't want to build a weak card underneath there. You want a good foundation. So then once we do that, we'll make sure a final time that we can read and write to the SRAM reliably. And then we'll move on from there. Okay, so let's create some functions for reading and writing to SRAM. So let's just put them in here for now, and later we'll move them probably to their own file for the driver code for the SRAM, but right now we'll just put them right here. So we want to return void for right now anyway, and it's IO board. And so I usually define a SRAM writing and functions with the name of the chip was 70 V05, and then this will be the write. We'll do the write first. So the write, you have to specify an address, and 16 bits is plenty for us on that. So we'll just do it like an M address so we know. And then we're also got to specify some data, and it is an 8-bit variable, and we'll call that M data. All right, so there's our function for that. So let's do the write. So the write's probably going to return the data, but we'll just do void for right now. Use a global variable to contain the data that we read. All right, and this only gets an address. Whoops, I don't know why I want to capitalize that. All right. Okay, so there's our functions. So let's do our prototypes while we're here thinking about it. Get that out of the way. Okay. Now, we already have a write function defined here, kind of in longhand, if you want to call it that. So we'll just cut that out of there. And bring it down here and put it into the write. Okay. So then we're going to have to bring this into the code. So instead of manualizing it here, that's the data. So we bring that down here. All right. And then we need the address. So we got to come up here and get our set address out of there right here. We don't need that in there now either. And we'll bring that down here. So that's kind of the first thing you do. All right. Equals address. Okay. So when you call this function, you input the address, comma, the data, and it puts the address into the address register, and then it enables the chip and it sets the direction, selects write, sends the data onto the bus, finishes the function, the operation, and exits. All right. So that's a write. And so the read, we'll just copy the same thing here and modify it for the write. All right. So the address is the same. Chip enable is the same. The direction becomes the opposite. And the read write becomes the opposite. And this gets switched around so that it's reading. And then we use PMD in 1. Okay. And then read write goes back to 1, stays 1, however you want to say it. The direction is the same, and then we deactivate the chip. So that's our read. All right. So we have to define address. I think that's what it wants. Identifier data. Oh yeah, so we have to do our global here, especially for this one. So we have to define it up here. Right here. And that's a uinteger8. mdata. And just go like that. And then we have to put it to make it global. We bring it up here to the header file. And we're going to put it right in here. And we're going to make it external. Okay? And we'll do the same thing with the address too. Oh, might as well just copy that whole thing right here. Just like that. Right. And then back up here to make it a global. All right. So we'll save that just in case the power goes out or something. Never know. It has happened. All right, so we got everything going on here. Do a test compile to make sure that we did okay. All right. Looks like we did good. Okay, so now let's set up to do a test. So let's write to the SRAM and then read it back and display it on the LED port. See what we get. Kind of a simple test to begin with. So, we got to go to our main function, which we're already in. And so we're coming down here and we initialize everything. And so let's do one right here. All right. So we're going to write to memory. Okay. So the address is going to be 0. We like 0. And the data is going to be like 57. Huh? But we're going to do it hexadecimal so we don't have to convert it. And so we're going to write 57. And then we're going to read 57. Read 0. We're going to write 57 to 0, and then we're going to read it and display it on the port and see what happens. Okay, read 0. Okay. So now we're going to activate our port function, and instead of variable A, we're going to grab this global variable here, mdata. See, because mdata, we're putting the data from the memory into mdata here. So we'll come back up here, and right here is going to be mdata. All right, so we should see 57 on the port. So another thing we have to do first is we have to go over to our interrupts, and we have to turn off setting this LED here because it's going to interfere with us writing on there. So we probably might not need that anymore anyway. So let's put our note here for the delay, because we have to put a delay in there here later on. All right, so that should work. Main brain's still writing to address 0, and that's going to cause an interrupt. Okay, we'll see what happens. We'll roll with it and see what happens. Okay, let's go look and see what it looks like on the scope. And we don't have anything. Oh! So let's get the scope probe out over here and look at some waveforms and see what's really going on. Okay. So let's check, just make sure the board's enabled. Okay, so it's low, that's good. So then the next thing we want to check is the chip enable, which is pin 5 here. 1, 2, 3, 4, 5. So that's the chip enable, and that looks appropriate. Then the next one is 6, which is read write. And we're getting a read and a write. All right. Then the next one is the output enable, which is 7. 1, 2, 3, 4, 5, 6, 7. And it's staying high. That means it's not reading. So did you guys not check up on me and make sure I was doing right in the code? Because I might have missed something right there. So then the next one, let's see, that's semaphore. So we just got to check our busy right here. And we're getting a busy. So we're getting interrupts. So it looks like our output enable, we got to go back to the code and check that real fast. Okay, let's go to our read function and make sure we got everything right. Maybe we'll find the problem. So we set the address, we enable the chip, We set our direction for a read. Our read write is 1 for a read. Then we do our data and we close it all. And so I suspect I messed up on here. I think I have to use a different register. So if we go to our data sheet here, this is what we used last time, I believe. And this is the one PMD read in is for the dual buffer mode. All right, and exclusively for reads, when the dual buffer bit is set. So that's the one we want. That's probably our problem right there. So let's put that bad boy in there. And then we'll send it and see what happens. All right. And if you look at our LED port, and the green LED being the most significant bit, it looks like 57 to me. So we got our functions going, and so now I changed a few things, so I'll go over that with you. I changed the setup on the clock to make it the spec on the microcontroller is for 100 MIPS, which is half of the frequency, which is 200 megahertz for the internal clock. So I set it up to where the oscillator was set up, configured to give us 100, which it works out to be like 105 MIPS. And that way we're in spec. You can overclock it. You can overclock it by a lot, but it takes more power. It runs a little hotter, and it's not recommended by Microchip. So this doesn't have to be a super fast board. So we'll just set it at the spec, and it's the high end of the spec. So I mean, 100 MIPS isn't nothing to laugh at. So another thing I did was I configured the PNP to generate the right pulse so that we don't have to bit bang it. And because the bit bang way, it creates kind of a wider pulse and stuff. It's not like standard. And so I configured the PNP to generate that pulse. And then I had to do add a wait state to make the pulse a little bit wider. I think I added 2 wait states. So now is what we want to do is set up our scope and look at the signals when we're writing to the SRAM continuously, and main brain is doing it continuously. And then we will configure our interrupt and see if we can make our data right to make it wait until the busy signal is not asserted, and then write the data. So let's check that out. Okay, so first thing I changed was the clock. So this is a setting for the clock that puts it right at the 100. It's actually 105 MIPS, which is like a 210 megahertz core clock. So that's the specification. You can go higher, but it's not recommended. But you can overclock these chips pretty good. But this is the recommended maximum 100 MIPS specification. This is the setting that achieves that. It's actually 105. Okay, so then down here, we have the write. We're doing our write through our write loop, I guess we can call it, because it's looping over and over, writing to that 0 address in SRAM, and main brain's doing the same on its side, so we're going to get lots of write contention. And so I'm putting a small delay where it counts to 10 before it goes to the next one, just so the scope doesn't get crowded and we got some space to like watch the signal and stuff. All right, so let's, as you can see on the scope, that's the write cycle right there. Channel 1 is the busy signal. When it goes low, that means the data is invalid. And channel 2 is the chip enable. That's our complete function, write function cycle. All right. So you'll see some noise popping in there. That's my scope. That's not actually measuring the noise. It's just my scope. All right. And so then channel 3 is the actual write pulse. Now I've changed that down here. I'm having, I configured the PMP to generate that pulse because that's a more standard pulse. When we were bit banging it, that takes up a lot more time. So this makes a more standard write pulse. And I had to increase a wait state on the write pulse. So I'll show you this real fast. So if we put this back to a 0, you'll see the write pulse on the scope gets pretty thin. Let me see if I can pop some time on that. You can see that it's still a good write pulse, but it's pretty thin. And if you get going faster, then the SRAM might not be able to get it. So we want at least 1 here. Let's do a 1 and see how much difference that makes. We don't want to add any wait states if we don't have to. So that looks like a pretty good write pulse right there. So we'll stick with 1 actually. But that's how you can do that. We'll have to check and make sure the data is really being put in there every single time. And if not, we might have to increase this back to 2, but we're doing pretty good. So there's that. And so now let's enable our interrupt. Well, let's go over here to our interrupt and I'll show you what I did. So I increased the speed of the interrupt by doing the bitwise operations on all of these wherever we change the bits and the flags and our data and stuff. That makes it as fast as you can do it. It's like typically 1 instruction cycle to do this. When you do this up here, this takes more time. And for initialization, that's fine. But when we're doing an interrupt, time is of the essence. So you want the interrupt to be able to complete as fast as possible so that we can implement our data, our functions and stuff like that. So that's what we do. Once we get an interrupt, we set this flag that we created as a 1, all right? And then we wait for the busy signal to go high. Then we clear the flags and move on. So when this busy signal gets set, we come over here to our write function. Then you'll notice that the busy signal is generated when the chip enable goes low, which is good because it gives us a little amount of time in here to do our thing. All right, so we write our data and then we check to see if this SRAM busy is a 1. So if you notice over here, as soon as our interrupt is triggered, and we know that it's this interrupt on this pin, which is the busy signal, we set this variable to a 1. All right, so that indicates that we did get a busy signal. Now, we're still in interrupt here. So we wait until the busy signal goes high, and then we clear our flags and exit. And so that comes over here. So somewhere in this range, we get a busy signal and an interrupt. All right. So if you look at the scope, we're getting a busy signal and we're writing. Okay. So we're going to write data just normally. So we're going to check if this busy signal is set. And it is set if we have an interrupt. So if we have an interrupt and this is set, then we write the data again. If not, if there's no busy signal, then there's no interrupt and this is 0. So it skips over and we just have a normal write. But if there is an interrupt, that means that the busy signal was generated and the interrupt sets this to a 1, so we write it again, okay? And then after we write it, we set this back to 0 and move on, okay? So let's look at what this actually looks like on the scope. Okay, so then on our global interrupts here, if we make that a 1 to enable our interrupts and send it to the I/O board, and now you see that no matter how wide the busy signal, we do a write after it. So no matter where I stop it here, whatever the width of the busy signal, we're always writing outside of that. All right. So that you see that second pulse, that second write pulse, that is our pulse that we're adding in right here. So if there's no busy signal, there will only be one pulse because it's a valid write. Okay. So that's what the write cycle looks like with our interrupt routine in there. And that should give us reliable data. Okay, so you see how that worked with added in that interrupt routine. So if there's an interrupt, that means there was a busy signal, which means there was a contention, which means that both sides tried to write to the same memory location at the same time. So when that occurs, then we set a flag, that SRAM busy flag, and that's a global variable. So it changes globally in the program as soon as we write to it. So then the interrupt handler waits until the busy signal is deactivated or inactive, high, and then it exits the interrupt. And so that the global flag is set. And so then we were in the middle of a write in our write function. So then it checks to see if that flag is set. And if it is, then it writes again to the SRAM before it exits. But if there's no flag set, then it just writes once and moves on, which should mean, if everything works correctly, it means that there was no write contention. So it's just a normal write. So that's how we handle the dual port RAM. Okay, so I want to do one last test to verify that we can read and write properly to the SRAM without any problems. So, because we've changed a lot of code, we've done a lot of things. So let's just verify our read and write functions for the final time, and then we can move on. So let's see, up here to our main loop. So we're writing to 0, main brain's doing that, so we're not going to worry about a busy signal. So we're just going to go to a different memory address, and we're going to write something a little different, like how about 90. We do a lot of 90s. How about 39? All right. And so then we're going to read it, and then we're going to wait a little while. We don't have, maybe we'll go a little faster. Let's see how it does though. And then read. We'll read it. All right. Read one. All right. And then, if you remember, we put what we read into this variable here, the global variable. And so we'll come up here. And so when we, oh, that's got to be a read. I almost forgot to change that. So that's a read. We're writing 39 hex to address 1. We wait a little bit. Then we read from address 1. And what we do, actually, I could have just used that, huh? And then what we do is we put it into our LED port and see if we see what we're supposed to. All right. There we go. That should work. All right, and then we'll send it to over to our I/O board. And there we go. Looks like we got it. All right, so we're reading and writing. Okay, so I think we're good to move on. Okay, well, that was kind of complicated. It was kind of tricky. I mean, I had to do a lot of work off camera. And in fact, I originally had some different code for that interrupt routine that I've tested and used on the motion board. But when I was looking at it with the scope, I just wasn't quite getting what I wanted. So one problem was that the setup, I had to change the setup on the rising and falling edge because what I got from Chat GPT was not what I was seeing on the scope. So they were backwards. Chat GPT made a mistake. So once I got the falling edge, because when I was doing the rising edge, that's always shifting back and forth, if you notice, on the busy signal. So that made everything jump with it. And it just didn't look right on the scope. I couldn't figure it out for a while. But it was because those were switched. So once I got it on the falling edge, which is stable, then it worked better, a lot better. But I still had to make some changes. And so I think this code is like the best code so far. So I might incorporate this code into the motion board code. I'll have to check that out and test it. But I think we got some really solid code here. So the only other thing is we have to do next is handle when MainBrain selects this board to transfer data, because MainBrain is also the main arbitrator of all the I/O cards. So it determines which card reads and writes when. So then that's an additional task for MainBrain. But that's what MainBrain is. It's the main processor, and it's going to handle the arbitration between the boards. So that's next on the list, is to generate an interrupt, which shouldn't be too hard because we already got an interrupt set up. So when that address A0 through 2 gets selected by MainBrain on our jumper up there, and it activates the buffers, then it also activates an interrupt in the microcontroller, and we have to determine what we want the microcontroller to do under that circumstance. And I might have to change, I might have to add some more wires. I might want to separate the interrupt and the from the actual buffer enable signals. I might need to separate them and get two signals going. I don't know. We'll look at that. That's what we're going to do next. So I will see you in the next video.